Thermodynamic geoengineering, the 93% solution to global warming. The right time and place for addressing the problem of global warming was 30 years ago. But since that hasn't happened, we need to start working on the problem today. Politicians and policymakers claim there are still a few years before we start crossing climate tipping points, beyond which most climate scientists acknowledge catastrophe lays, but that isn't the case. The analysis of David Wasdell, director of the Apollo Gaia project in 2014, showed we are already committed to in excess of 5.3 degrees of warming. The first chart from Wasdell's study shows on the bottom scale the cumulative CO2 emissions from 1870 onwards in gigatons of carbon, and to the left is the temperature anomaly relative to the period 1861 to 1880 in degrees Celsius, as well as the various representative pathways for greenhouse gas concentration trajectories adopted by the IPCC in 2014. The next chart changes the upper scale from gigatons of CO2 to parts per million and draws a straight line through the Charney sensitivity the IPCC has almost exclusively focused on, from 0 through the dotted line indicating 560 parts per million, which is a doubling of the pre-industrial CO2 level and its intersection with 3 degrees Celsius. The sensitivities the IPCC are overlooking are the Hadley, Hansen, and Earth system sensitivities. These additional feedbacks compress the quantity of CO2 necessary to produce a given temperature, and the next graph explores Wasdell's relationship between sensitivity and the total carbon for a given temperature target, starting with 2 degrees Celsius. The solid horizontal bars show the carbon budget in blue and the carbon overshoots in red. As is apparent, we are already into overshoot for a warming of 2 degrees per the vertical purple band on the left side of the graphic. Overshoots for a 1 degree target, where we are today, are shown next. For a target of 1.5 degrees, the aspirational goal of many at the Paris COP, there is no climate budget, and the overshoots range between 31 and 394 gigatons of carbon. The three targets together show that instead of having a supposed carbon budget of 200 gigatons, we are into an overshoot of 464 gigatons. The gray bar represents the non-CO2 greenhouse gases. The latent but unfulfilled promises of the international community concerning climate change are represented by the dark purple band. The business as usual scenario is represented by the violet band. Below is the projected equilibrium temperature of 5.3 degrees Celsius we are committed to with current greenhouse gas levels, because the effects of the non-CO2 greenhouse gases mask effects of atmospheric particles that will end with the cessation of fossil fuel burning. The last chart by Gavin Smith, director of the NASA Goddard Institute for Space Studies, confirms Wasdell's analysis, which is now 5 years old, but it wasn't until a few months ago that the University Corporation for Atmospheric Research, one of the most respected and quoted entities in the climate field, in its latest iteration of its Community Earth System model, bumped its estimate for a doubling of carbon dioxide by 33% to show 5.3 degrees is in fact the future confronting us. Global warming is the accumulation of trapped solar energy. It makes all the difference in the world, though, where in the atmospheric oceanic system this heat is situated. The science shows that between 1991 and 2016, the oceans gained 12.1 zettajoules of heat per year. This equates to 388 terawatts of heat each year, or 21.5 times more energy than is consumed by humanity every year. Between 1844 and 1854, the English scientist James Prescott Joule worked on the problem of the relationship between the amount of work spent to bring about the liberation of heat and the amount of heat liberated by the work. He used a paddle wheel device submerged in a heat-insulated vessel attached by a series of pulleys to a weight to determine 1 calorie is equal to 427 kilograms dropped 1 meter, which in turn is 4.19 watts. Dropping a 1 kilogram weight 427 meters accomplishes the same result. The average temperature of the ocean at a depth of 1,000 meters, where the water is at its maximum density, is universally about 4 degrees Celsius. The average temperature difference between the tropical ocean surface of 27.5 degrees Celsius and 4 degrees C is 23.5 degrees C, analogous to a potential hydraulic head of 10,035 meters, where the head warehoused behind a conventional hydroelectric dam. Carnot efficiency reduces the height of this dam to 326 meters, 20 meters higher than China's Jinping 1 Dam, the world's highest, and this potential exists throughout the tropics. About 1900 years earlier, Hero used an eolipile to show how heat could produce work by raising a weight. Thermodynamic geoengineering is the embodiment of both Joule's experiment and the eolipile, and is the process whereby heat can be converted to work and the balance can be consigned to deep water. In order to convert the surface heat, it must be accumulated, which is accomplished with a triangular energy island 735 meters aside. The consignment is accomplished by a heat pipe that can move heat at a speed approaching that of sound, much like the eolipile. The driver for this movement is the pressure produced by boiling the working fluid and the partial vacuum as the vapor is condensed. The physicist Melvin Pruitt, using a U.S. Department of Energy proprietary program called OTEC-exec, determined the net efficiency of the conversions of such a device is 7.6%. 7.6% of the 388 terawatts of annual warming is 29 terawatts, or twice what we are currently deriving from fossil fuels. The island is in turn comprised of 55 sections, each with sides of 73.5 meters. The bottom of each segment is punctured by holes through which waves are directed by wave accumulators into a channel that collects the hydraulic pressure. The top of each section is bordered by walls 3 meters high, and each apex accommodates connectors that joins the sections together and allows them to move through 45-degree range of motion. The interior of the section is segmented into lengths of 7.35 meters each. A number of supports hold up the top and a platform for the solar panels. The hydraulic pressure of the waves is collected in a series of pipes that convey the hydraulic pressure to a converter at the back of the island. A frame for the solar panels sits atop the supports that in turn support the solar panels. Some of the sections have windmills. 250 megawatt energy island produces about 200 megawatts of OTEC power and another 50 megawatts of wind, wave, sea current, and solar power. This is a rendering of an overview of a segment containing a windmill and a circumnavigational view of the same segment. Next is a circumnavigational view of the entire island. And a perpendicular section of the island highlighting the evaporators that convert the surface heat into a vapor and tanks that collect hydrogen. A heat pipe conveys the latent heat of evaporation into deep water where the vapor drives a turbine that drives a series of generators to produce electricity. The electricity is converted to hydrogen and oxygen by a series of electrolyzers. The spent vapor is transferred to a series of condensers where the vapor is turned back to a liquid which is pumped back to the surface to complete the cycle. About 92.4% of the heat of warming is transferred by the condensers into the deep as the latent heat of condensation. The oxygen, hydrogen, and liquid return to the surface where the oxygen is passed through the evaporators to prevent biofouling. The hydrogen is collected in tanks for transshipment, and the working fluid is passed back to the evaporators to complete the cycle. Not only does this process cool the surface, it reduces sea level rise due to thermal expansion of the ocean and ice melting. The coefficient of expansion of water is half at 1,000 meters it is at the tropical surface per the following graphic. And heat moved to deep water isn't available to melt ice at the higher latitudes, nor is it available to drive hurricanes or produce amplified storm surge, nor produce atmospheric rivers, desertification, or wildfires. To transfer energy produced in mid-ocean to markets, it must be converted to an energy carrier. The super green hydrogen fuel process, invented by Greg Rau and his team from Lawrence Livermore Labs, fits this bill perfectly and sequesters carbon dioxide while neutralizing ocean acidification. In the published paper Negative CO2 Emissions Ocean Thermal Energy Conversion, Dr. Rau and I demonstrate for each gigawatt of electric power produced by thermodynamic geoengineering each year, roughly 13 gigawatts of surface ocean heat will be directly removed to deep water while producing 130,000 long tons of hydrogen, avoiding 1.1 million tons of CO2 and consuming and storing as dissolved mineral bicarbonate approximately 5 million tons of CO2. This planetary cooling of about 2.6 gigawatts would avoid the biophysical and land use limitations posed by methods that rely on terrestrial biology. 2012 paper World Ocean Heat Content and Thermospheric Sea Level Change 0 to 2,000 meters, 1955 to 2010, a team from the National Oceanographic Data Center estimated the volume warming of the ocean to a depth of 2,000 meters was 0.09 degrees Celsius, and that if this heat was instantly transferred to the lower 10 kilometers of the global atmosphere, it would result in a volume mean warming of this layer by approximately 36 degrees Celsius. They said this won't happen because the Earth's climate system simply doesn't work like that. But the only thing that's stopping such a release is the carbon dioxide blanket that is trapping warming heat in the atmosphere and ocean. With policies like a tax on carbon, we would actually be hastening the demise of humanity unless we come up with an alternative approach to dealing with the heat accumulating in the ocean. Researchers from the International Energy Agency in 2018, however, found that the oceans were accumulating 13 zettajoules of heat at the time, which equates to 384 terawatts, or 21 times the global energy consumption. In which case, instead of the potential release of 36 degrees into the atmosphere, estimated in 2012, we could be, by extension, looking at closer to an atmospheric warming potential of 102 degrees Celsius. In the recent Washington Post article, Energy 202, if the U.S. doesn't change course, carbon emissions will rise again in the 2030s. Former Energy Secretary Ernest Moniz says the report by the EIA underscores the need for massive government research for a hard-to-decarbonize industrial sector, including investing in technologies that convert electricity into clean burning hydrogen fuel for factories, or that captures carbon before it reaches smokestacks. These two technologies uniquely meet and exceed these two goals, and what's more, it isn't government research that is needed. It is development of technology that is already on the drawing board that is required, and there is no reason why this can't come from a private sector eager to capitalize on the economic opportunity, motivated by the social implications of global warming. No consideration of energy cost can be made in the absence of a comparison with fossil fuels, which dominate the sector and are subsidized worldwide to the tune of $500 billion and are producing an annual environmental cost of doing business of $4.7 trillion. Energy is a $6 trillion business, and it will take years to replace the existing infrastructure, so our job as entrepreneurs and as proponents of a replacement technology is to produce the prototype that can prove the existence of a viable alternative and to scale and multiply that solution. The objective is to provide investors and bankers with a climate solution in which they can put their trillions. This graphic is from the MIT thesis of Shailesh Muralidharan entitled Assessment of Ocean Thermal Energy Conversion. It shows that OTEC has the highest capacity of the technologies and has amongst the lowest levelized cost of the renewables and is on par with advanced nuclear power. The study is for conventional OTEC, but Muralidharan noted a subsea condenser architecture such as thermodynamic geoengineering costs a third less than the conventional approach. The study shows each doubling of the size of OTEC plants reduces cost by 22%. This graphic shows the progressively cheaper cost of thermodynamic geoengineering as the plants become larger. The assumptions are the 100 megawatt plant is 33% lower than the base cost of a conventional 100 megawatt OTEC plant, estimated by Luis Vega of the University of Hawaii at $4,000 a kilowatt hour per the next graphic. The base cost of $2,650 a kilowatt hour is from the study on the cost-effective ocean thermal energy conversion power plant published in Offshore Technology by Srinivasan and Sridhar. The cost assumptions are from the Muralidharan thesis. The annual revenue is prorated on the existing cost of energy of $6 trillion for 18 terawatts compared to 29 terawatts for the conversion of the heat of warming to work. It has to be noted in all cases the cost of these plants is less than the annual environmental cost of business with fossil fuels, even without subsidies. Therefore, thermodynamic geoengineering is effectively too cheap to meter. This graphic is from the seminal work Ocean Thermal Energy Conversion Primer by Luis Vega. It shows first that ocean-going plants are cheaper than land-based efforts. His primer says the economic evaluation of OTEC plants indicates that their commercial future lies in floating plants of approximately 100 megawatt capacity for industrialized nations and smaller plants for smaller island developing states. He said, unfortunately, the size of the experimental plants, less than 0.3 megawatts, is about 2 orders of magnitude less than the size required for commercial systems for industrial nations, which is 100 megawatts at a minimum. In 2013, Lockheed Martin and the Rhinewood Group in China announced they were considering a 10 megawatt plant at a groundbreaking effort at a cost of $1 billion. Ultimately, this effort foundered due to the cost, amongst other problems associated with conventional OTEC, which will be addressed later in this proposal. Suffice to say, a 30% decrease in cost with subsea condenser architecture would have helped that effort and will benefit the partners and investors of this proposal. The Catch-22 is a prototype will likely cost in the $700 million to $1 billion range, but this has to be measured against the $100 billion climate pledge in 2009 by the industrialized countries to aid the vulnerable countries like the small islands developing states, which would be the greatest beneficiaries of technology that provides energy that reduces sea level rise. In 2017, the industrialized countries contributed $70 billion to these nations, but none of that money is relieving sea level rise. And technologies like negative emissions CO2 OTEC that sequester emissions in the course of business have to be measured against direct air capture efforts that are currently removing CO2 at a cost of $100 to $200 a ton and are shooting for $30 a ton. These efforts are being funded mostly by the petroleum industry, who see throwing a few dollars at direct air capture as a way of sustaining their industry. Burning natural gas to sequester CO2 is magical thinking that defies the second law of thermodynamics, which is the blueprint for thermodynamic geoengineering. Entrepreneurs should have no problem raising $1 billion when the return is 4 orders of magnitude greater, and the viability of the planet might well be dependent on their effort. The competition. This graphic from the paper Negative CO2 Emissions Ocean Thermal Energy Conversion shows the potential global power generation capacity and hence energy production potential for renewable energy sources in likely developable locations. Subsequent to the publication of this paper, it was determined OTEC's potential is actually 29 terawatts, as shown above. Not shown is nuclear power, which James Hansen, Kerry Emanuel, Ken Caldera, and Tom Wigley claimed in a 2015 Guardian article paves the only viable path forward on climate change. Mark Jacobson of Stanford contradicts this claim in his 2019 paper, Evaluation of Nuclear Power as a Proposed Solution to Global Warming, Air Pollution, and Energy Security, which broke down the risks associated with nuclear power into 2 categories. 1, the risks affecting nuclear's ability to reduce global warming and air pollution, and 2, the risks affecting nuclear's ability to provide energy and environmental, aside from climate and air pollution, security. The exponent of this pitch faults nuclear power on the basis of thermodynamics, because it's only 33% efficient and therefore adds an additional 2 terawatts of heat to the system for every terawatt of power generated. Flanner, in his paper Integrating Anthropogenic Heat Flux with Global Climate Models, shows that nearly all energy used for human economy is at some point dissipated thermally within Earth's atmosphere or land. The energy that doesn't fit this pattern is trapped heat converted to work. Typically, energy production contributes about 1% of the energy flux being added by anthropogenic greenhouse gases. The problem is, the rule of 72, which is a simple way of determining how long an investment will take to double, given a fixed annual rate of interest, says at a warming rate of 3%, China's energy growth rate is about 3.7%, it would take only 24 years for the rate of growth to double. So in only 150 years, the amount of waste heat being produced by thermal processes like nuclear power would be the same as we are currently experiencing with global warming. The other competition for investment dollars on the environmental energy front to those shown in the first graphic in this section are solar radiation management and carbon dioxide removal. Solar geoengineering has been suggested as a potential means to counteract anthropogenic warming, since volcanic eruptions have been demonstrated to have a cooling influence. The paper, The Climate Response to Pulse versus Sustained Stratospheric Aerosol Forcing, by a team from the Carnegie Institution at Stanford, points out, however, direct extrapolations from volcanic eruption observations provide limited insight into into impacts of potential stratospheric aerosol geoengineering. And David Keith has acknowledged that there are serious concerns about solar geoengineering, both in terms of environment and politics, and Chicago geophysicist Raymond Pearhumbert has called such schemes barking mad. As has been noted above, direct air capture as a carbon dioxide removal scheme is expensive, and as Mark Jacobson suggests, carbon capture technologies can cause more harm than good. Even if you have 100% capture from the capture equipment, it is still worse from a social cost perspective than replacing a coal or gas plant with a wind farm, because carbon capture never reduces air pollution and always has a capture equipment cost. Wind replacing fossil fuels always reduces air pollution and never has a capture equipment cost, he says. And with thermodynamic geoengineering, there are additional environmental benefits that should be subsidized. Kevin Anderson of the University of Manchester and Glenn Peters of the Centre for International Climate Research say removing carbon dioxide emissions from the atmosphere to prevent more warming from becoming catastrophic may be a fool's game amounting to a moral hazard par excellence. Extrapolating from the chart above, showing we have added about 1,000 gigatons of CO2, and based on Klaus Lackner, Director of Arizona State University's Center for Negative Carbon Emissions goal of $30 a ton, it would cost $30 trillion to sequester the CO2 we have accumulated since 1780, which doesn't stack up well compared to slide 41, which shows that between $32.5 trillion and $76.9 trillion invested in negative emissions OTEC, NEOTEC, we can have 30 years of twice as much energy as we are getting from fossil fuels and can sequester all of the CO2 accumulated to date in as little as 7 years to boot. Slide 43 shows that solar has by far the highest potential of the renewables. So besides the fact it doesn't address sea level rise, surface heating, drought, or wildfires, cost is the determining factor in the move to a sustainable future. Idaho Power has reported the record low solar price of 0.02175 per kilowatt hour for 120 megawatts of solar power in March 2019. By comparison, the cost for NEOTEC is between $0.004258 and $0.01008, which is between half to a fifth the cost of the low solar price per slide 47. And this cost should be subsidized for the environmental damage it would avoid, which is currently $4.7 trillion. Real competition to NEOTEC and thermodynamic geoengineering is conventional OTEC, that is a heat dilution solution that moves masses of water from the deep to cool the surface, which is problematic for the 5 reasons listed below. Heat moved to only 100 meters is back at the surface within months. Therefore, the relocation provides no warming respite. This was evidenced during the so-called warming hiatus, where the trade winds shifted much of the heat of warming into the western Pacific, but still within the mixed layer. Surface ocean heat is akin to an oil slick. Inserting a fire hose beneath the slick only causes the slick to move away from the nozzle, and in this analogy, it is dispersed towards the poles. As soon as the heat migrates out of the OTEC zone, shown in the OTEC map above, it becomes unproductive and can never be recovered. This heat can and will melt the ice caps. This image is from a paper, An Assessment of Global Ocean Thermal Energy Conversion Resources with a high-resolution ocean general circulation model by Rajapalan and Niehaus. It shows that a cold water upwelling rate of 20 meters a year, equating to a power rating of 30 terawatts, the tropical ocean surface is cooled as much as 4 degrees C over the course of 1,000 years. But that cooling is offset by equivalent warming at the higher latitudes and along the productive fisheries of the east coast of South America. With an efficiency rating of only 2% as calculated by the Ocean Thermal Extractable Energy Visualization Team comprised of researchers from Lockheed Martin, Florida Atlantic University, University of Hawaii, and the National Renewable Energy Lab. The maximum amount of energy that can be produced annually without affecting the thermohaline circulation is only 7 terawatts. This is close to a quarter of the theoretical Carnot efficiency for these temperatures because half of the heat is lost to the evaporators and condensers with the conventional approach. Pruitt showed the loss to the heat exchangers is only 4 degrees instead of the 12 with the cold water pipe design, and that a vertical column of vapor 1,000 meters long gains 5 degrees due to the gravitational effect on the column. Furthermore, the pumping parasitic losses are 30% less for a heat pipe, so 7.6% of the heated warming can be converted to work to produce 29 terawatts. Hypothetical problems. Some claim reducing our consumption of energy is the answer to global warming, but that isn't the case. The more of the heat of global warming that can be converted to useful work, the better off we will be. Others claim that it is too risky to depend on the ocean to provide the energy the world needs. The petroleum industry has years of experience now in that environment, and the best locations for thermodynamic geoengineering are in the intertropical convergence zone where hurricanes don't form. The Joint Group of Experts on the Scientific Aspects of Marine Environmental Protection, a body that advises the United Nations on the scientific aspects of marine environmental protection, concluded in 2019, thermodynamic geoengineering to cool surface waters could effectively reduce warming associated with climate change, but implemented at a large scale, such effects could be temporary, regionally heterogeneous, and present the type of termination risks usually associated with solar geoengineering approaches. The justification for this codicil was a 2015 study produced by a team of researchers from Stanford University that has been rebutted by the Natural Energy Laboratory of Hawaii and others. The Stanford study used a model that boosted the background diffusivity of the top 1,000 meters of the ocean surface by a factor of 600, which is physically impossible. There isn't enough power on the planet to produce such an upheaval. Most OTEC researchers have considered an upwelling approach that moves large volumes of water from the depths to cool a condenser that produces the power of the heat engine. This is 40% as effective as thermodynamic geoengineering, 33% more costly, and produces the regional heterogeneous effects the UN warns of. The upwelling proponents assume, owing to the very low thermodynamic efficiency of OTEC cycles, the overall OTEC process does not remove heat from the ocean, which doesn't accord with the laws of thermodynamics. A conversion of ocean heat to work performed on land is by definition an extraction of heat from the ocean, and the only way ocean heat can be safely extracted from the ocean. The Natural Energy Laboratory of Hawaii has demonstrated that the termination risks of OTEC are unfounded, and there is no earthly reason to terminate a process that produces the energy the world needs while cooling the surface, limiting sea level rise, storm surge, wildfires, drought, replaces fossil fuel emissions, sequesters carbon dioxide, and neutralizes ocean acidity. Thermodynamic geoengineering is neither temporary nor heterogeneous. It sequesters global warming heat for 225 years and then recycles it 13 times, allowing the waste heat of the conversion of the heat to work to dissipate to space over the course of 3,000 years. It provides a 150 generational global warming hiatus. It is homogeneous in that it cools the entire surface at the expense of a minuscule warming of the ocean, which ultimately returns to its pre-industrial temperature. Warm water is buoyant, but this buoyancy is overcome by a heat pipe that moves heat through the phase changes of a low boiling point working fluid. The heat capacity of the ocean is 3 orders of magnitude greater than the capacity of the atmosphere. To keep the heat of warming within the tropics and yet cool the surface, the 1.2 degrees of warming that has occurred to date, the ocean would have to be diluted 100,000%. This would take place within only a tenth of the ocean's surface, therefore 10 times the 100,000% dilution is ultimately required. In a 2007 U.S. patent filing, the theoretical physicist Melvin Pruitt of Los Alamos National Laboratory, with the aid of a computer program OTEC exec, determined the efficiency of a heat pipe design, like thermodynamic geoengineering, is 7.6%. The efficiency of conventional OTEC is only 3%, and with conventional OTEC, the heat of warming never moves deeper than the mixed layer of the ocean, where the diffusion rate is 1 meter a day, and therefore the heat resurfaces in a few months, which is why the approach allows the heat of warming to move rapidly to the poles, provides no respite from warming, and gives rise to erroneous notions like the overall OTEC process does not remove heat from the ocean. Hurricanes also cool the ocean surface, but they only move heat into the mixed layer, which is why 3 different hurricanes can occur along the same path during a single hurricane season. The diffusion rate of water from the ocean depths to the bottom of the mixed layer is about 1 centimeter a day, or about 4 meters a year. Heat moved a kilometer down therefore diffuses back to the bottom of the mixed layer in about 225 years, then moves through the mixed layer in about 3 months. So in total, heat sequestered in the ocean is back on the surface in about 225.3 years, where to prevent as much as 102 degrees of warming, it is recycled back to deep water to produce more work. Given a 7.6% efficiency, the conversion of warming heat with thermodynamic geoengineering, it will take 13 cycles of 225.3 years, or about 2,930 years to recycle and convert all of the heat of warming to work, and to safely let the waste heat of those conversions to dissipate to space, neither of which are temporary nor heterogeneous. Elon Musk has pointed out, somebody could say, and in fact people do, the battery packs are really expensive, and that's just the way they'll always be, because that's the way they've been in the past. But you just have to think of clever ways to make materials and combine them into the shapes that are much, much cheaper than anyone realizes, he says. A lot more energy is packed into a cubic meter of the tropical ocean than reaches its surface. The top 2.5 meters of the ocean hold as much heat as the entire atmosphere above it. To stabilize the atmosphere, we must move surface ocean heat into deeper water and convert a portion of that heat to the energy 10 billion people will need by 2050. For example, it takes 100,000 square miles of solar panels to produce 18 terawatts of energy, whereas it takes only 10,500 square miles of the ocean's surface to produce 29 terawatts with thermodynamic geoengineering, which is cheaper than solar power, requires no storage, and harvests energy from no one's backyard, from a minimal surface area. 80% from OTEC and 20% from the waves, wind, and solar energy that flows over and below the platforms. Ocean heat conversion to work is the social challenge and economic opportunity of the century. A lack of aggressive steps aimed at addressing climate change are putting the world at grave danger. Improving global access to clean energy would be a positive step toward reducing global conflict, and as the late Robert Smalley, 1996 Nobel laureate in chemistry, in his Terawatt Challenge pointed out, energy is the answer to the next 9 challenges facing mankind.